Hey everyone, Justin here. I'm back in the lab for Science Club. Today, we're studying bacteria under a microscope. So I need to check out this sample. The microscope says each turn of the knob increases the zoom by a factor of 10. Here's the original size. It's just a blur, way too small to see. Turning the knob once makes it 10 times bigger. I'll turn it again. That's 100 times the actual size. Still pretty small, though. One more turn makes it another 10 times bigger. That's 1,000 times bigger than the original. Now I can see the bacteria. Each turn multiplied the zoom by 10, just like repeated multiplication. How can we represent repeated multiplication? Exponents. So let's try writing the zoom amounts as exponential expressions. At the start, we hadn't turned the knob at all, so there were no 10s to multiply. Let's come back to that later. With one turn, the zoom was 10 times bigger than the original. That's 10 to the power of 1. With two turns, it was 10 times 10, or 10 squared, which is 100. For three turns, it was 10 times 10 times 10. That's 10 to the third power, or 1,000. But what about that first row? Maybe we can use what we filled in to figure it out. Look at the last column, the total zoom. What happened to the zoom each time we turned the knob? The zoom was multiplied by 10. How can we work backward to find the first row? Well, what operation undoes multiplication? Division. To move up the chart, we can divide by 10. So we'll take the zoom from the second row, 10, and divide it by 10, and that tells us the zoom is 1. That makes sense. Multiplying by 1 doesn't change anything. It's the original size. But what about the exponent? Each time we turned the knob, the exponent increased by 1. So working backward up the chart, what happens to the exponent? It decreases by 1. Using this pattern, what do you think the exponential expression should be in the first row? All the expressions had a base of 10, so let's keep that the same. Moving up the chart, the exponents decrease. 3, then 2, then 1, so next is 0. So this expression is 10 to the power of 0, and its value is 1. In fact, this pattern works no matter what number or variable the base is. Any base to the power of 0 equals 1. Let's try an example with different types of bases. Pause the video here to evaluate these exponential expressions. Each expression has an exponent of 0, but a different type of base. Part A has a positive base, 5. Part B has a negative base, -9. Remember, when the negative is inside the parentheses, it's part of the base. And part C here has a variable base, x. These different bases don't change the answer, though. They're all equal to 1 because of the 0 exponent. I don't know about you, but I had no idea 0 could be an exponent. Do you think we could keep working backward into negative exponents? Here's part of the chart from my microscope with a few rows added to the top. Moving up from 10 to the power of 0 will decrease the exponent by 1 each time. 1 less than 0 is -1, giving us 10 to the power of -1. Then we'll have 10 to the power of -2 and 10 to the power of -3. To move up in the value column, we divide by 10. What's 1 divided by 10. 1/10. 1/10 divided by 10? That's 1/100th. And 1/100th divided by 10? 1,000th. Wow, those values are small. When we had positive exponents, the microscope zoomed in, making the bacteria look bigger than the original size. With negative exponents, it's like zooming out, and the bacteria would look even smaller. First 1/10th the size, then 1/100th, then 1,000th of the original. Check out the values of the pairs of positive and negative exponents. 1 with -1, 2 with -2, and 3 with -3. What connection do you notice between the values in each pair? Pause the video and write it down. Each expression with a negative exponent has a 1 in the numerator and the value of the matching positive exponent in the denominator. That means the value of the negative exponent is equal to the reciprocal or flipped version of the value of the corresponding positive exponent. So, an expression with a negative exponent is rewritten by taking the reciprocal of the expression and then making the exponent positive. We can use this to rewrite 6 to the power of -2 as an equivalent expression with a positive exponent. We take the reciprocal, creating a fraction with 1 in the numerator. Then we put the exponential expression in the denominator, changing the -2 to a +2. That gives us 1/6 squared. Now it's your turn. Rewrite each expression as an equivalent expression with a positive exponent. Remember, variables are placeholders for numbers, so a variable base works the same way as a numeric base. Pause the video to try these out. For part A, 4 to the -3rd power, we'll take the reciprocal, giving us a fraction with 1 in the numerator. Write the original expression in the denominator, but change the exponent from -3 to +3. That gives us 1/4 cubed. The process is the same for part B, k to the -5th power. Take the reciprocal, then put the base k in the denominator, and change the -5 to +5. That's 1/k to the 5th power. When the base is a number, we can take it one step further and evaluate the expression. We already rewrote 4 to the -3rd power as 1/4 cubed. Now, let's evaluate the denominator. What's 4 cubed? 4 times 4 times 4, which is 64, meaning the final value is 1/64th. Notice that the result is positive, even though the exponent was negative. That's because the negative exponent does not determine the sign of the answer. It just tells us to take the reciprocal instead. Let's do one more together, evaluating -2 to the power of -5. First, pause the video to rewrite this with a positive exponent. Remember, since the negative sign is inside the parentheses, it is part of the base. So keep everything in parentheses together. To rewrite, take the reciprocal and change the exponent from -5 to +5. Now, pause the video to evaluate the denominator, -2 to the 5th power. This represents -2 times itself 5 times. That's 32, but is it positive or negative? It's negative. Remember, when a negative base is raised to an odd exponent, the value is negative. This means -2 to the -5th power is equivalent to 1/-32. But when a fraction has a negative in the numerator or denominator, we usually move the negative sign in front of the fraction giving us a final value of negative 1 over 32. Here, we got a negative value, but that came from the negative base and the odd exponent, not the negative exponent. We've got time for one last example. Evaluate these two expressions. Pause the video to try them on your own. 2 to the negative third power can be rewritten as 1 over 2 cubed. Evaluating 2 cubed gives us an answer of 1/8. Negative 4 to the power of negative 2 is rewritten as 1 over negative 4 squared. Negative 4 squared is negative 4 times negative 4, which is positive 16. That gives us a final value of 1/16. Here, the value is positive even though the base was negative. It's important to take these problems step by step and identify the base and exponent to evaluate them correctly. Thanks for joining me in the lab and checking out those bacteria today. With your help, we discovered any base to the power of 0 equals 1, and negative exponents create reciprocals with positive exponents. I'm headed back to my lab station, and while I do that, you finish up your guided notes and complete practice levels 1 through 3. Until next time, keep questioning, keep calculating, and remember, when exponents are negative, they flip things upside down. See you next time. Hey.